Hi, everybody. Thanks very much for coming. I'm Bob Harmon. I'm in the Department of Physics and Astronomy here at Ohio Wesleyan. And that's right. Oh, woo! And as I like to say, I'm the campus astrophysicist. And I'm here today to tell you about the total eclipse of the sun that is happening right here on the OWU campus on April 8th. The next time that'll happen on campus, a total eclipse like that, is September 14th of 2099, which actually makes this kind of early because any given location on Earth, it's about 400 years on average between total solar eclipses. So we're doing all right there. So mark your calendars now. All right, it's always important to start with some safety information, namely, never stare at the sun when it is only partially eclipsed. To do so can cause permanent eye damage, and your retina doesn't have pain receptors, and so you won't feel it when you're damaging your eye. So don't do that. To view it safely, you'll need certified eclipse glasses. Sunglasses are not nearly good enough. Look for ISO 12312-2, and sometimes there's a colon 2015 at the end of that. It is safe and encouraged to look directly at the sun during the brief time it's totally eclipsed. So the idea is you got your cool eclipse glasses on, and then you see the last vestige of the sun disappear, and then you take them off, and it's like, whoa, right at that point. You don't want to leave them on during totality. OWU and Perkins Observatory are making certified eclipse glasses available free to the campus community and also to the public. For the public, it's one per person present, and then they can spend $1 for each additional pair, which goes to Perkins Observatory. For the campus community, we're not charging at all. They can be picked up at the information desk in the Hamilton Williams Campus Center, and we've got a stash here, actually, if you want to hang around afterwards and get some eclipse glasses. All right, so let's talk about the basic facts regarding eclipses. So you've probably seen something like this before, where you've got the sun and the moon, and you sort of draw a line, if you will. There's no up or down in space, but you draw a line from the top of the sun to the top of the moon, top of the sun to the bottom of the moon, and then vice versa. This is really in 3 dimensions, so you'd rotate the whole diagram around. And what we find is that the moon has both a penumbra, a lighter part of its shadow, and the umbra, the darker part of its shadow. So the idea is, suppose you were floating in space in the penumbra. So you're like an astronaut right there. And you draw a line of sight to the sun. Some lines of sight to the sun are not blocked by the moon when you're in the penumbra, but other lines of sight to the sun are blocked by the moon. And so at that point, the moon is partially covering the sun. You will be seeing a partial eclipse if you're in the penumbra. And if you're on Earth and you're in the penumbra, that's when we're seeing a partial eclipse. That's how this eclipse will start. We'll start out in the penumbra. Meanwhile, if you are in the umbra, then every single line of sight that you could draw to the sun has the moon in front of it. So that's when you're seeing total eclipse, where you see the sun completely covering the moon. And if you're in this region right here, beyond the tip of the umbra, region D here, that's the antumbra. And there, what happens is you'd be seeing what we call an annular eclipse, where the moon doesn't look big enough to completely cover the sun, and so you'd see a bright ring of sunlight around the moon, which is cool, but total eclipses are much cooler, and that's what we're going to get to see this time. All right. So I want to play a little game here, and if you already know the answer because perhaps you're taking a class from me, you're not allowed to play, all right? So I want folks to say how far you think the moon is away from the Earth. So let's make a scale model. Here we have a standard 12-inch globe, and this green ball, moon's made of green cheese, right? This 4 or so inch ball, 3-inch ball, is about the right size to be the moon in comparison to the Earth. So if you put the moon in front of North America, it would go from like New York to Las Vegas or so. And so what I'm going to do is start walking, and I want you to tell me when you think I've got the moon far enough away from the Earth. So turns out my feet are about a foot long. That's where the word foot comes from. So I'll start walking along, stepping off a foot at a time. So 1, 2, 3, can I do this? 4, 5, 6, 7, 8. Burn. 9, 10, 11, 12, 13, 14, 15. Burn. 16, 17, 18, 19, 20, 21, 22, 23, 20. Burn. 24, 25, 26, 27, 28, 29, 30, 30. Oh, very good, yes. Ding, ding. Ding, 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 ding. Yeah, about 30 feet in this scale model. So the moon is 240,000 or so miles away from the Earth. The Earth's 8,000 miles across, so it's about 30 Earth diameters away. Most people underestimate how far away the moon is, right? So when the moon's making its orbit around us in this scale model, it's making this 30-foot in radius circle around the Earth every month. So this is a properly scaled model of the Earth-Moon distance, as opposed to what you see in books, just to make it easier to draw and so forth, where they look like they're much closer together than that. So let's look at, again, a diagram that shows how an eclipse works. So if we have an eclipse of the sun, here we've got the moon passing in between the Earth and the sun. And there's this cosmic coincidence where the sun is about 400 times larger than the moon is, but it's also about 400 times further away than the moon is, which means they look almost exactly the same size in our sky, which is why we can get eclipses where the moon just pretty much perfectly blots out the sun. And as a result of that, what that means is that just the very tip of the moon's umbral shadow makes it to Earth. Now, sometimes we get an annular eclipse, and when that happens, it's because the moon's orbit isn't perfectly circular. Sometimes the moon's a bit closer to us, sometimes a little bit further from us. And so it turns out in most eclipses where the moon passes in front of the sun fully where you are, you get an annular eclipse instead of a total eclipse, because most of the time the moon's a bit too far away. But guess what? On April 8th, it's close enough to get a full-on total eclipse of the sun. Now, this diagram right here shows it properly scaled again, shows how far the moon really is away from us, just how long that shadow is, finally reaching Earth. Meanwhile, you can also have lunar eclipses. In that case, it's the moon passing through the Earth's shadow, which is a lot easier to do because the Earth's shadow is a lot bigger and longer than the moon's shadow is. All right, I want to talk about how lunar phases work. So a lot of people seem to think that lunar phases are caused by the shadow of the Earth on the moon, but that's lunar eclipses. So here I've got a styrofoam ball where one side is white, the other side is painted black to represent the lit and unlit halves of the moon, right? So half the moon is always lit by the sun, the side turned towards it. The other half is unlit by the sun. The lunar phases are caused by how much of the lit versus the unlit side that we see. So if we see only the unlit side turned towards us, anybody know what do you call this phase of the moon? That would be new moon, all right? And so then as the moon, it's like you're taking a class from me. So as the moon orbits, then you start to see more and more of the lit side of the moon. And so I'll kind of do it like this for you. So now you can see you're starting to see some of the lit side of the moon, and it has that kind of, it looks like a banana, so to speak. That's kind of the classic thing people draw for the moon. What phase of the moon is that? That's crescent, and in fact we call it waxing crescent. If you're seeing more and more of the lit side every day, then it's a waxing phase. So you get waxing crescent, then you get to where you can see like a half moon. And we call that first quarter because it's a quarter of the way through the phase cycle, even though it's a half moon as we see it. You get past that, you start to see more of the lit side than the unlit side. That's called gibbous. So we get waxing gibbous. Finally, the whole lit side is turned towards you. That's full moon. And then we go through waning gibbous, third or last quarter, waning crescent, back to new again. Okay? Having said all that, we can deduce that eclipses of the sun can only happen at one particular phase, namely the phase when the moon is in between us and the sun, so that the unlit side is the side that's facing us. So in other words, an eclipse of the sun can only happen at what phase? New, yeah, only at new moon, whereas an eclipse of the moon, there we have to be in between the sun and the moon, so we would turn around and see the fully lit side of the moon, and so eclipses of the moon can only happen at full phase. So here's a video that I made. This is an exercise we set up for Astronomy 110. My colleague, Dr. Barbara Andrek, invented this, and I liked it so much that I use it too. So we set up a bunch of cups with balls just like that one, painted half black, half white. That yellow thing there is supposed to be on the board. That's supposed to be the sun way, way far away, 400 times further away than the moon, but the room's not that long. So what I did is just spin around, making a video of all the balls. And so you can see them go through all their phases. So it's new moon. And then you imagine the moon keeps orbiting. Now there's some angle between it and the sun. So now we got waxing crescent. First quarter. Waxing gibbous. Now I'm facing opposite the sun. So that's where I would see full moon. The full moon rises about the time that the sun sets, and sets when it rises because it's on the other side of the sky. Waning gibbous, and the box that the styrofoam balls were in. Third quarter, waning crescent, and finally new moon again. So I always want my students to react to something like this with an ooh, ah. So let's see what we do. Pretty good, pretty good. I'm going to go for better here. So on a count of 3, 1, 2, 3. Pretty good, pretty good. I'm going to give that an A. Very good. I'm proud of y'all. So, okay, why don't we have an eclipse of the sun every time the moon is new? Why don't we have an eclipse of the moon every time the moon is full? It's because Earth orbits the sun on a plane. We call that the plane of the ecliptic because the moon has to be in that plane for an eclipse. The moon orbits the Earth also on a plane, but those two planes are tipped by an angle of 5.2 degrees to one another. They intersect along a line called the line of nodes, and in order for there to be a good enough alignment between the Earth, moon, and sun for an eclipse to happen, the line of nodes has to be pointed to the sun to a high enough precision. So most of the year, what you have is that at new moon and full moon, you miss, the shadows miss. In other words, the moon kind of passes above or below the sun so that you don't see an eclipse. In other words, if you could see the new moon, you can't, but if you could see the new moon, it would miss the sun in the sky. It doesn't block it. And given how far apart they really are, it's easy to see that it's pretty precise alignment that you're going to need in order to get the shadows to fall properly. So most of the year, that's what happens. But there are 2 times of year called eclipse seasons where the line of nodes is close enough to being lined up with the sun that when the moon is full or new, it's pretty much in the plane of Earth's orbit and is able to block the sun from our view for a solar eclipse, or our shadow falls on the moon for a lunar eclipse. Those are about 35 days long each. So if the direction of the line of nodes stayed constant, then the eclipse seasons would be 6 months apart. It's actually more like 5.5 months because that line of nodes itself is slowly rotating around with a little bit more than 18-year period. And so as a result, the eclipse seasons, as we call them, drift around the calendar over the years. So you can see here in 2024 why we're in an eclipse season now. And in fact, the moon is waning gibbous right now. It was full just a few days ago. And there was, in fact, what we call a penumbral lunar eclipse that day. The moon didn't get into Earth's umbra, but it did pass through the penumbra. Wouldn't look that spectacular, but there was a lunar eclipse. And then on April 8th, well, then we get a really good alignment, and we're going to get a total solar eclipse. So let's talk some more about that. So here is a diagram that illustrates, again, the moon is too close here, but here is the moon's umbral shadow just reaching to Earth's surface there, surrounded by the intersection of the moon's penumbral shadow, the lighter part with Earth's surface. If you're anywhere within the penumbra, you're seeing a partial eclipse. And if you're in that narrow band, you have a chance for the umbra to pass over you. And while the umbra is passing right over you, that's when you're seeing the total eclipse. So this is actually the path of totality for this eclipse. First we'll be in the moon's penumbra. Then for 2.5 minutes we'll be in the umbra, seeing totality. Wow, that's a true ooh, ah, at that point. And then we'll be back in the penumbra again for a while. Meanwhile, back in October, you might remember there was an annular eclipse of the sun. It was only partial here, and it was cloudy that day. But there, the moon was a bit too far away, but folks along this path were able to see annular eclipse in that case. I would travel for a total eclipse. Some people would travel for an annular eclipse. Nah, I'm not going to spend that money. But for a total eclipse, oh, totally. And you're here. You don't need to go anywhere. So here is a zoom in on the path of totality. You can see the green center line, and then you can see blue is the northern limit, red is the southern limit. This is from the National Solar Observatory. If you Google National Solar Observatory eclipse map, or you use that QR code on your phone, it'll take you there, and you can click and zoom on that map and like find your house and see exactly how long the eclipse is going to last at your house or your friend's house where they're inviting you to come to the eclipse party or anything like that. So here is an animation from greatamericaneclipse.com of the moon's umbral shadow passing over our part of the country. So let's watch there. You can see there's Indianapolis, there's Dayton, there's Marysville, there's Delaware right there, and we're in totality. Ooh, ah, it's amazing, it's amazing. Oh, we're not in totality anymore, right? And you can see that if you were watching there, the moon's shadow is moving almost 2,000 miles an hour over us at that time. So it's a combination of the moon moving in its orbit and us turning on our axis that causes that path of the moon's shadow like that. So a couple weeks ago, I gave a talk at the Westerville Public Library, and I used the NSO eclipse map to figure out how long they would be in totality. Westerville is very close to the southern limit. In fact, whether you see any totality in Westerville depends on what street you're on. And so I say, like, well, get in your car if you're in Westerville. So the library itself will get 17 seconds of totality at that location. Get in your car and drive. How much totality you get depends on how close you are to the center line, to the center line of the eclipse. That's where it's longest. In Ohio, at the center line, we get a little bit less than 4 minutes of totality if you're right near the center of the eclipse. Notice that even this line right here, you've already got 2 minutes of totality. How much totality you get increases very rapidly as you move towards the center line when you're near the edge. And so even there, it's 2 minutes. Well, how about at Selby Stadium, where I want everybody to gather to have a group experience of seeing it. It's really important, it's really good to see an eclipse as a group because people start screaming, people start shouting, some people might even start crying. If you've seen photos, you might imagine that you know what it's going to be like to experience totality, your imagination is wrong. You really have to experience it. It's really something else. So we'll talk some more about that as we go along. But here in Selby Stadium, why we'll be getting 2 minutes, 36.4 seconds of totality. So quite a bit more than even like Westerville, for example. Here's the eclipse details for Selby Stadium. There's a site timeanddate.com where you can put in your coordinates or some city names and so forth. They'll give you all the details. So the partial eclipse begins at 1:55 and 54 seconds. And totality begins at 3:11 and 36 seconds. Maximum eclipse is 3:12 and 54 seconds. Totality ends at 3:14 and 12 seconds. Then we're back to partial phases again until 4:27 and 7 seconds. Well, the seconds don't really matter. The real thing to keep in mind is totality is in between 3:11 and 3:14, a little bit more than 2.5 minutes in there. So that's when you should be like, oh, I got to be sure I'm paying attention right now. This is a simulation. It's not supposed to look super realistic, but it's a simulation from eclipse2024.org. For Westerville, but it's essentially going to be the same here, to say where you need to look. So during the eclipse, the sun will be at an azimuth of about 220 degrees, which means it's in the southwest, and an altitude, angle above the horizon, of about 50 degrees, so a little more than halfway up. And this makes it very well placed for observation in Selby Stadium. In other words, if you're kind of looking down the axis of the football field towards the goalposts on the south end, then the sun will be like about there. So what we're going to have everybody do is gather in the visitors' stands, because that'll be a great place to look at the sun during totality. And then also, we're going to set up some telescopes. The Astronomy Club's going to help with that, so that people are able to see the sun projected safely. Some will have eyepieces where you can look at the sun through them, building up to the excitement of totality. The gates will open at 1:30 p.m., then we'll have totality, 3:14, that'll be done. And then it'll be time to go home, basically, because it's kind of all downhill after totality. That's the show. You've seen the partial phases beforehand, getting more and more excited. Wow, totality! Oh, back to partial phases. I mean, that's cool and all, but the athletes need to practice now anyway or whatever. So what are you going to see when you see the totally eclipsed sun? So this is the solar photosphere. The photosphere, the sphere of light, is the layer of the sun that we normally see. This is the, if you're just looking at it with your eyes, bright yellowish white layer of the sun that we normally see. And you can see a sunspot group there. There's actually a very large sunspot group on the sun right now, which I think I can just barely see with the naked eye, not by looking straight at it. What are we never going to do? We're not going to stare at the sun, right? Yeah, we're not going to do that with our naked eyes. But with the eclipse glasses on, perfectly safe, I think I can just barely make out a spot group on the right edge of it, but it may be because I knew it was there because I projected an image of it with Kyle, our lab manager, earlier in the day. Yeah. Kyle will be our point person during the event at Selby Stadium. Above the photosphere is a layer that we call the chromosphere, the sphere of color. This is emitting red light due to hydrogen gas. That technical detail is it's a little bit higher in temperature than the photosphere. The photosphere is like 5,500 degrees Celsius. The chromosphere is more like 10,000 or even higher degrees Celsius. It emits much less light than the photosphere does because it's much less dense, but the light it emits is mostly this red spectral line of hydrogen where excited electrons are jumping down from the third excited state down to the second excited state and giving off light of a very specific wavelength that is red in color to our eyes. Now, we will have a telescope with an H-alpha filter on it that will allow you to see a view like this by looking through the eyepiece. So think in terms of visiting that telescope before the eclipse, because the cool thing is, here I turned up the brightness on that image. So when you see it through the telescope, it'll look more like the prior image. So look right here towards the edge of the sun. Do you see that kind of like looks like a little wispy, maybe lick of flame or something like that there? That is what we call a solar prominence. And that's chromospheric material emitting that red light that's being supported by solar magnetic field lines. And during totality, when the moon is covering the photosphere, blocking it from our view, you'll be able to see what look like little red licks of flame sticking around the edge of the moon. Those are prominences. That's the only time that you can see the chromosphere with your naked eye, is when the photosphere, which is much brighter, is blocked from our view. So the cool thing would be that if you go to that H-alpha telescope, hydrogen alpha telescope, you can see the prominences through that. And then during totality, you can be like, oh yeah, I saw that prominence. There it is again. Meanwhile, this is the solar corona, which will surround the sun during totality. I mean, it's always surrounding the sun, but in other words, you'll see it surrounding the moon, covering the sun there during totality. And this is really something that you need to see with your own eyes. In other words, you've probably seen photographs like this. Nice enough, but your eye has much more dynamic range than any camera does. And so it's just impossible to photograph this and make it look like it will look to your eye. It is ethereal. You see those it looks like kind of like silken threads in there. Those are actually magnetic field lines. What you're seeing is this layer of the sun called the corona, the outer atmosphere, nothing to do with the virus. Corona meaning crown, so it's like a crown around the sun. That's electrons and dust particles that are scattering light from the photosphere back to our eyes. Electrons, charged particles, spiral around magnetic field lines, so they concentrate around them. And so those things that look like threads, you're actually seeing those are tracing out solar magnetic field lines, and they just look like fine silk. It's just amazing what that looks like. You really have to see it with your own eyes. Then, at the end of totality, really before too, so here's my advice, okay? So the sun is almost totally eclipsed. You got your glasses on. You see the last bit of the sun go away. Take off your glasses. Enjoy totality. At the end, all of a sudden, you're going to see what's called the diamond ring effect, where you begin to see the photosphere peeking out from behind the sun again. Now, in 2017, when I saw totality then, I didn't expect, it was my first time, I didn't expect this to be my favorite part of the show. It was so beautiful. That little bit of photosphere, again, cameras and displays can't show this, so searingly bright. And at the same time, you could see the corona and the licks of flame, so to speak, the chromosphere there. And in fact, as I was looking at it, it suddenly dawned on me, stop it, right? Because it was so beautiful, I was starting to stare. What are you not going to do when the sun is at all uncovered, the photosphere is at all uncovered? You're not going to stare. You are certainly not. And so enjoy it and immediately stop enjoying it, right? It'll be plenty enough to burn into your memory just from that brief moment. You know, it's not any more dangerous per se to look at the sun during an eclipse when it's partially eclipsed than it is anytime. It's always dangerous to stare at the sun. The problem is that when the sun is partially eclipsed, it looks cool and unusual, and you're tempted to stare. So you've got to tell yourself, you've got to force yourself, don't stare at it. Don't even try to look at it when it's partially eclipsed. Don't tempt yourself. But here, I'm going to say, you know, enjoy the diamond ring for a very brief moment and then put your glasses back on or turn away from it. Don't stare at it. I can't say that often enough. All right, I'm going to show you a video from a YouTube channel called Veritasium. That is run by Derek Muller, is the name of the gentleman who will be narrating this video. And he's a physicist, and this is a wonderful channel. He does all kinds of videos about science and math and so forth. I highly recommend it. He went to the 2017 solar eclipse, and he made this video about what it's like to view it. And I want you to notice how emotional people get. And I also want you to realize that he's a physicist, and so he knows exactly what's going on, but he hadn't seen totality before. And so you'll see him going like, what is happening, right? This is so wrong. Same thing happened to me. I know what's going on during totality. There's no mystery there. But when I actually saw it for myself, I'm like, what is happening? And this will be you too, right? And this will be many, many people surrounding you. That's why there's going to be whoops and cheers and maybe even tears and so forth. So check it out.
It's August 21st, 2017, the day of the total solar eclipse. I'm in Madras, Oregon. The skies are clear. This is my sky tracker. It's meant to move the camera with the sky, so it sort of compensates for the Earth's rotation. That should help me keep the sun in shot as the eclipse is taking place.
Drove up from LA, so
We have first contact. This is C1. You can just see the moon entering on the top right side. We are 17 minutes out from totality, and I think the light is starting to change. I think it's getting noticeably dimmer. There's a bit of like a cold wind coming in from this side. Can you guys feel it? It's getting kind of cool, and it's getting darker. I'm really excited. Now that the sun is about 90% covered, I'm seeing much sharper shadows. Normally shadows, they're a little bit fuzzy because the light from the sun is coming from a whole bunch of locations, but now because it's coming from basically one little sliver of the sun, the shadows are all getting very, very sharp.
That is weird and eerie. Oh my God.
Oh
weird.
my God. Ah!
Guys, look around. Just try looking around.
This is insane right now. Oh, this is just unbelievable. What?
Oh my God.
What is happening? This is absolutely insane.
There's the beads.
I feel like it's hard to breathe. Oh. Oh my God. This is so totally creepy.
Oh my God, the sun.
Oh my goodness. This feels so weird.
Look at the sunrise, Derek. It's every direction.
Oh my goodness. There's like sunset, sunrise, every direction. People are going nuts. This I did not expect. I don't know what I expected, but...
Oh my God.
This just looks so wrong. You can see these prominences, the solar corona coming out, the top left and right and the bottom. I can see Venus directly above me.
Yeah. You can see the stars.
Oh, what? What is this? What? I just don't even know. We are inside totality. I am kind of speechless. It is just unreal right now. Isn't it? It's totally nuts.
Oh.
What?
Poke the hole in the sky. But it's so dark. 360 sunset.
Time and ring.
Our excitement that the sun is back. I'm gonna pop the solar filter back on.
Yeah. So we're reading.
I just want to say a huge thank you to my Patreon supporters. You made it possible for me to buy a flight here and for the equipment that kept my camera tracking with the sun and the solar filters on the front, and yeah, basically everything I needed to get here and see this total solar eclipse. So thank you so much for supporting me. You make it possible to keep doing the things I love doing and making these videos.
So he had a camera that he had set up and so forth. Here's my advice. It's actually difficult to get a good photograph of the eclipsed sun. A phone camera doesn't stand a chance of making a really good photograph of it. The way to view this eclipse during totality is on your retinas, not on any kind of screen. So there will be professionals that take photographs of this that you'll find easily online and everywhere. That'll be a much better remembrance of what you saw than any pictures that you try to take. The seconds during totality are precious. You don't want to waste them looking on a screen. You want your retina to be enjoying that. Burn it into your memory that way. That's my advice to you. I hope you will take it. I took my own advice back in 2017, and I'm going to take it again here in 2024. This eclipse will actually likely be better than the 2017 eclipse because this eclipse, the sun is near what we call solar maximum. Its magnetic activity, sunspots and so forth, are around a peak. That will make the corona even more beautiful than it was in 2017. He mentioned being able to, oh, I'll get to that in a second. So one thing he didn't mention, because he didn't have trees around, and in Selby you're not going to have trees around, but when you view the sun during an eclipse and you're around some trees, so maybe if you're somewhere where some trees are before you head over to Selby, the spaces between the leaves can act like little pinholes. And those act like lots and lots of little what we call pinhole cameras. And so this is a photograph of the effect that you get from that. You get lots of images of the partially eclipsed sun from all those pinholes. So that's pretty cool looking. He also mentioned that, you know, oh, I see Venus, I see stars, and so forth. So here is a simulation of conditions during totality from a program called Stellarium. You can download it for free at stellarium.org for Mac OS, for Windows, for Linux. It's cross-platform, and it's absolutely free. It's a sky simulator that lets you play around with what the sky looks like from any place on Earth at any time and so forth. So I set it for Delaware during the eclipse, and you can see that at that time, you were not going to be able to read it from back there, but this is bright Jupiter that will be on the left side of the sun. This is even brighter Venus that will be on the right side of the sun, and I'm not sure how well to be visible, but right next to one another, lower down in the sky closer to the horizon, if you see two brightish things, that's Mars and Saturn. Notice that you can see that the planets are all kind of in a line with the sun like that. The reason is because all the planets orbit the sun in very nearly the same plane. And during an eclipse, you can see that for yourself, right? There's the solar system, the sun, planets laid out before you. No guarantee on this, but there's a comet, Pons-Brooks, that might be visible during totality, which would be pretty cool too. Add a comet to the mix here. Not sure, but just those planets will be cool enough. So be sure to appreciate that aspect of what you're seeing. Again, your shadows will start to get strangely sharp, which is an eerie feeling. You'll notice that it's getting cooler. You'll notice the temperature drop. Those are all just pretty remarkable phenomena, but totality is the show. You just really have to appreciate that beautiful, beautiful eclipsed sun. So I hope that you're getting excited for this, because I certainly am. I'm really hoping we get good weather. We're good people. We deserve good weather for this. Absolutely. Even if partly cloudy, well, you just have to hope that the clouds don't get in front of the sun during totality. I hope, I hope, I hope. So that's what I got. Thank you very much. Happy to take questions if anybody has one. We have a mic runner, so Kyle will hand you the microphone.
Thank you so much for this, Robert. You are an amazing gift to this campus and our community. I have read that birds and other animals get very confused during a totality. Could you speak to that?
Sure could. Yeah, they do, right? Because birds are like, huh, it's evening already? Well, I guess I'll go home to roost. And so birds start roosting. Yeah, wildlife are very confused because they think night is falling. Back in 2017, I saw the eclipse with Elaine at the home of Qingshuan Wu, our former Chinese professor who had moved on to Western Kentucky University in Bowling Green. And she brought her dog Mei Mei out to see the eclipse. Now, I will say Mei Mei was completely unimpressed. He was just like, meh. But other wildlife, yeah, it's very interesting. You might notice that. I mean, I won't know if we'll see that in Selby, but it is true that any creature that roosts at night or whatever, then they think, well, what's going on here? I will say, don't expect it to be as dark as night. We're really talking about kind of twilight darkness here. In the video, you might remember somebody was saying, wow, sunsets all around the horizon. What they're talking about there, clearly the sun isn't setting there, but we're in the umbra, but we're surrounded by the penumbra still. We're surrounded by areas that are not. And so brighter skylight is coming in from there, and the sun looks reddish, right, when it rises or sets, and that's because the sunlight is passing through more atmosphere. Dust particles in the air and air molecules scatter more bluish light, more short wavelength light than they do long wavelength light, reddish orange. So the light that gets to us from the sun at sunrise and sunset has a higher proportion of red, orange, yellow light than green, blue, violet, because that light has an easier time making it through the atmosphere. Same deal for the moon when it rises. That's why it looks reddish when it rises and sets. Now, what's happening here is we've got that light coming in from our surroundings, but it's near the horizon. And so again, there's a greater fraction of the red and orange light coming from our surrounding area to us than other colors. And so it looks like there's a pretty orange glow all around the horizon. And people describe it as, wow, it's like sunrises and sunsets all around the horizon. So around the sun, it's this weird bluish purple color. And then around the horizon, it's orange color. So it's just lovely. So do stay, right? In other words, stare a lot at the totally eclipsed sun, but spend some time looking around, enjoying that view. Look at Jupiter, look at Venus, try to find Saturn and Mars, maybe a comet. Just soak it in is what it comes down to. And don't use your phone.
It seems like really long odds that the sun and the moon and the distances and the sizes would align in such a way that this sort of miraculous event would take place. Mm-hmm. Have there been any other observations on other planets or other examples where science has observed something similar to what we experience here?
So we're the only planet that has a moon that just happens to look in our solar system, that just happens to look almost the same size as the sun in our sky. So on Mars, for example, the rovers have actually photographed eclipses of the sun by Mars's two little tiny moons, Deimos and Phobos. but they're not big enough in Mars's sky to totally cover it. So you just see, oh, look, it's a potato in front of the sun, because those moons kind of look like potatoes, basically. On Jupiter, if you look at Jupiter through a telescope, you can see easily, even through binoculars, you can see the 4 Galilean moons, the ones that Galileo discovered back in the early 1600s. And you can very often see that you can literally watch them in orbit. They move fast enough. And you'll often see a little black dot on Jupiter, which is the shadow of one of those moons. And if you were hovering in the Jovian atmosphere at that moment, you'd be seeing a total eclipse of the sun. That's that moon's umbral shadow on Jupiter. But it wouldn't be as cool as the ones we get to see, because those moons look much bigger in Jupiter's sky than the sun does. And so it's not this cool effect where it's just covering it so you can see all that corona surrounding it like that. So just by coincidence, we get the coolest total eclipses in the solar system. For other planets around other stars, we just don't have the technology to know that at this point. And take this opportunity while it lasts, because the moon is slowly getting further away from Earth by a couple of centimeters every year. And in about 1 billion years, it'll be too far away for there to be any more total eclipses anymore. So be sure you see totality sometime in the next 1 billion years.
In the chance that it does get really cloudy here,
Yeah.
would you recommend just driving somewhere where it's not? I don't know how practical that would be. I know that
That's a very good question, right? Like, what if you know that the forecast is very poor for here? So for one thing, if it's going to be raining or overcast, we're not going to do the event at Selby. It'll still get dark for a few minutes. That'll be cool enough, but it's not the show, right? It's not as amazing as totality. Being actually able to see it. That's what happened to me in China back in 2009. I was bitter for a long time, still kind of bitter because that was more than 6 minutes. But then I saw 2017 and life was good again. But in any case, if you're mobile, yeah, consider that, but also be aware that, boy, a lot of people are going to be trying to do the same thing. So it'd be like, wow, set out really early in the morning, because you could be easily caught in traffic for a long time. But yes, in fact, I'll admit it, I'm actually not going to be on campus during the eclipse. Why? Well, Elaine and I want to be really sure we see totality, so we're going to be on this chartered bus that, if it's clear in Ohio, I hope, we're going to go to Wapakoneta near the center line to see a little bit more totality. If it's not clear in Ohio, we're going to go to Memphis near the path of totality, and then look at the weather, not us, but the organizer of the trip, look at the weather and drive somewhere where we think it will be clear. So yeah, I'm not going to be here, but I want you all to really experience this. So, so yeah, that's my answer is, yeah, consider that. Drive a little if you think you can pull that off, if the weather's looking bad, because it is really nice to see totality, as a matter of fact. Yes. All right, thanks again, everybody, for coming.